And because there are two principles involved here that you should know that help a lot in drawing these pictures. Principle number one is that two integral curves cannot cross at an angle. Two integral curves can't cross I mean by crossing at an angle like that. I'll indicate what I mean by a picture like that. Now, why not? This is an important principle. Let's put that up in at least in a white box. They can't cross because if two integral curves are trying to cross, well, one will look like this because it's an integral curve because it has this slope, and the other integral curve has this slope, and now they fight with each other. What is the true slope at that point? Well, the direction field only allows you to have one slope. If there's a line element at that point, it has a definite slope, and therefore it cannot have both this slope and that one. It's as simple as that. So you can't, the reason is you can't have two slopes. The direction field doesn't allow it. Well, that's a big, big help, because if I know here's an integral curve, and if I know that none of these other pink integral curves are allowed to cross it, how else can I do? Well, they can't escape, they can't cross. It's sort of clear that they must get closer and closer to it. You know, I'd have to work a little to justify that, but I think nobody would have any doubt of it who did a little experimentation. In other words, all these curves join that little tube and get closer and closer to this line y equals x. And therefore, without solving the differential equation, it's clear that all of these solutions, how do they behave? As x goes to infinity, they become asymptotic to, they become closer and closer to the solution x. Is x a solution? Yeah, because it's an y equals x is an integral curve. Is x a solution? Yeah, because if I plug in y equals x, I get what? On the right-hand side, I get 1, and on the left-hand side, I get 1. 1 equals 1. So this is a solution. Let's indicate that it's a solution. So analytically, we've discovered an analytic solution to the differential equation, namely y equals x, just by this geometric process. Now, there's one more principle like that, which is less obvious, but you do have to know it. And so they're not allowed to cross, that's clear. But it's much, 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 much less obvious that two integral curves cannot touch. That is, they cannot even be tangent. Two integral curves cannot be tangent. I'll indicate that by the word touch, which is what a lot of people say. In other words, if this is illegal, so is this. Can't have it. You know, without that, for example, it might be, I might feel that there would be nothing in this to prevent those curves from joining. Why couldn't these pink curves join the line y equals x? You know, it's a solution. They just hitch a ride, as it were. The answer is they cannot do that because they have to just get asymptotic to it, ever closer. They can't join y equals x because at the point where they join, you'd have that situation. Now, why can't you have this? That's much more sophisticated than this, and the reason is because of something called the existence and uniqueness theorem. Existence and uniqueness theorem which says that there's through a point x0, y0, that y prime equals f of xy has only one and only one solution. One has one solution. In mathematics speak, that means at least one solution. It doesn't mean it has just one solution, okay? That's mathematical convention. It has one solution, at least one solution, but the killer is only one solution. That's what you have to say in mathematics if you want just one. One and only one solution through the point x0, y0. So the fact that it has one, that's the existence part. The fact that it has only one is the uniqueness part of the theorem. Now, like all good mathematical theorems, this one does have hypotheses. So this is not going to be a course, I warn you, those of you who are theoretically inclined, very rich in hypotheses, but you do have to, the hypotheses for this one are that f of xy should be a continuous function. Now, you know, like polynomial signs, stuff like good, should be continuous near, in the vicinity of that point. That guarantees existence, and what guarantees uniqueness is the hypothesis that you would not guess by yourself. Neither would I. What guarantees the uniqueness is that also its partial derivative with respect to y should be continuous. Should be continuous near x0, y0.